All right, I'm nice and loose after office hours, ready to do this recording again. Hopefully I won't make a mistake and have to do it a third time. This is the practice problem from lecture 23's summary sheet. 100 moles per hour of a 50-50 ethylene glycol water mixture is separated in a single stage liquid-liquid extraction using 200 moles per hour of furfural as the solvent. Predict is the key word. This is a predict type problem. We talked about that in video 2. In other words, I have the feed set. I know that my feed is 100 moles per hour of a 50-50 mixture, and my solvent flow rate is set, and my solvent composition is also set. I've also set that I have one stage only, one mixer settler. So everything is set except what I actually get out of this thing. So a predict type problem has 3 steps, very similar to distillation and absorption stripping. It's an alternation of material balance, equilibrium data, until you've found what you need to solve. So step 1 is going to be performing a material balance to find the mixing point. Material balance to find the mix point. To find mix point. Oops, mix point. Now, the mixing point is not in the process flow diagram that I've drawn here, but it's implicitly implied that when I mix two things, if I just take what the composition would be, I can find where that mixing point is. And then ideally, I'd want the mixing point to be somewhere within this two-phase region, because if it's not, if the mixing point is out beyond the equilibrium curve, then I only have one stage. I'm not going to get phase separation in the settler, and I haven't separated anything. I now just have a mixture of 3 things instead of 2. So to find the mixing point, I'm going to use my graphical method that I showed you in video 1. So I need to plot the points of the things that I am inputting to my mixer settler. So 50% solute, 50% diluent is on the 0 solvent line, so over here, corresponding to 50% ethylene glycol is, remember, the horizontal line. 50% water is this line that slopes down like so. And then 0% furfural is this horizontal line, which is all the way to the right side of the triangle. 100% furfural is this vertex. And if I connect them with a line, I will see the potential mixing points that I have. The mixing point has to lie along this black line that I just drew. So one way to do it would be to kind of eyeball it using the lever rule. I know that it's 2/3 solvent. So if I'm starting at feed, I know that I have to go 2/3 the length along this line until I reach my solvent. But another way to do it is to just simply work out what the composition of one of the things is. So I could say that the flow rate of the mixing point is 200 plus 100, or F plus S. It's equal to 300. And then I could solve for one of the compositions. So let's do a solvent balance. Solvent coming in is 200 times 1, because that's the mole fraction of solvent in the solvent stream, plus 100 times 0 is equal to 300 times XS of the mixing point. Let's solve that one equation, one unknown, and I would find that XS of the mixing point is 2/3, 67%. And then the other 2 things, if I wanted to do it, it'd be about 1/6, exactly 1/6, so 67.7%, or whatever that happens to be. All right, so I know my one coordinate, the solvent, which is furfural, has to be 67%. So I have to be somewhere along this line. And if I extend this line visually, this is where my mixing point is. So M is right there. If I wanted to quickly double check and make sure that my work is right, I said it was going to be 1/6 or 16.7%. So that's 16.7 ethylene glycol, 16.7% furfural. I'm sorry, 16.7% water is there, which works with where my mixing point is. Thankfully, my mixing point is within the 2-phase region, so I can draw my tie line. Remember, there's infinite tie lines in this space, so I would just want to draw one that looks like it fits in, kind kind of reasonably approximating what the slope would be if I had that tie line. Something like that looks pretty good. Again, doesn't look too out of place. And where the tie line intersects the equilibrium data on the both sides is where my compositions will be of my extract and raffinate phases. The side that's closest to water, the side that's closest to diluent, remember is called the raffinate. Raffinate composition, not raffinate, raffinate. And the side that's closest to the furfural is the extract. I'm going to use where these points are to find what the compositions of the phases are. So we'll start with the raffinate. The water coordinate is this line. So up to 52% water. So this is X of the diluent in the raffinate stream, 0.52. The solvent, the furfural, is about 10%, 0.10. And then the ethylene glycol is just 100 or 1 minus the sum of these two. So 0.38 is what I get. And then I could just double check, make sure that's about 0.38. So I'm reasonably confident that I did that correctly. The extract compositions are going to be, let's see, the ethylene glycol is about 10%, so 0.10. The solvent, I'm going to call that about 86%, 0.86. And the diluent then must be, by process of elimination, 4%. So quickly double checking, that's about 4% water up there. Okay, oh, I skipped the second step here, which I already did it, but I didn't write it. It is using the equilibrium diagram, using tie lines, equilibrium data, to find the composition of the extract and raffinate phases. Find compositions of extract and raffinate, of E and R. All right, again, I'm looking for the tie line that intersects my mixing point. So if I don't have it, I have to sketch it in, and then wherever it intersects, the tie line intersects the equilibrium diagram, that's where my compositions are going to be. The third and final step of solving this problem is using material balances again. Use material balances to find the flow rates of extract and raffinate, to find flows of E and R. Okay, so two unknowns, extract and raffinate. So I need two equations. My degree of freedom analysis would tell me that. Because I know that I have three material balances I can write, that means one of them is not going to be independent. So if I wanted to double check myself, I could try solving all three, but I want to caution you that the reason why you have three material balances is because you read these numbers off of a graph, and therefore you don't have the greatest amount of precision. So if you try to do all three material balances, you may find that they're slightly inconsistent, but please do not worry about that because they're based on numbers that you get. It should be reasonably close. So you should be within 5% error or so. And if you're any more than that, it means you either made a mistake in your material balance or you made a mistake in reading the graph. So I'm going to solve my material balances. I've got an overall material balance. So just doing a material balance on this mixture settler, I can say that F plus S is equal to E plus R. And earlier, I already worked out that F plus S was equal to M. So an easier version of this equation might just be is equal to 300 is equal to M. So E plus R is equal to 300 is an easier equation to solve. Well, I guess not really, because you can always just plug in 100 for F and 200 for S. But it's typically easier to do the material balances in terms of what the mixing point is. You'll see what I mean in a second. All right, so I have to choose. I have two unknowns in this equation, so I need at least one more equation, exactly one more equation to solve, and then another one to check, I guess, if I wanted to. I'm going to do the solvent material balance. So solvent coming in is 200 times 1. is equal to E times, let's see, 0.86 plus R times 0.10. All right, two equations, two unknowns. You can go ahead and solve this. Typically, I like to use substitution, so I'm going to substitute. I'll say that R is equal to 300 minus E. So I'll substitute and say 200 is equal to 0.86 times E plus 300 times 0.1. If I distribute the 0.1 as 30 minus 0.1 R, E, sorry, 0.1 E. And then collect terms. So 170 is equal to 0.76 E. And then solving for E, I get 221 moles per hour. Yeah, okay, so that gives me my extract. My raffinate is then 300 minus that, so 79 moles per hour. And that is the last thing I have to solve for. So I have now called this problem complete once I fill it in. Now keep a couple of things in mind, that this is a single stage, and you might look at this and say, well, if the goal of the problem is to reduce the concentration of solute in the diluent, we actually haven't done a very good job in a single stage. So we're still at 38% and 52%. So remember, what we're going to have to do from a process engineering standpoint is to send this to further stages if we had a design specification that was any lower than this. So 2 more stages. And we also now we've got a little bit of solute in our solvent. So we have to post-process this somehow. So that was a single stage liquid-liquid extraction problem. Next time we'll talk about multi-stage liquid-liquid extraction problems. And we'll talk about the 2 configurations that you can set these things up. So you can go cross-current, which is what this looks like, or counter-current, which is what an absorption/stripping problem was. So that's all for today. I will see you on Wednesday.